Good morning, students. Welcome to the virtual classrooms. We are studying related to the chapter number 7, chemical equilibrium. The one of the part of that chapter, that means the 50% of the chapter, chemical equilibrium, we did it. Today, we are going to start with ionic equilibrium, which is a second part of the chapter. We are going to study that means in those reactions, equilibrium will be established when the ion formations are taking place. Like if we take it as an example, HCl, it ionizes to H plus and Cl minus, but it never establishes the equilibrium in the solution. Whereas in the case of CH3COOH, it produces the ions of CH3COO minus and H plus, which will establish the equilibrium in the solution. So, first of all, we want to understand those concepts, that which substance will establish equilibrium, which won't establish the equilibrium, even when the ion formation takes place. Right? Again, when we are talking about the ionic equilibrium, it is necessary that we should understand that these ionic equilibriums are generally established by acid-base salts. Right? So, we are going to study within this chapter only related to acid, base and salts. Right? We are not going to study about the rest of the compounds or other ions which are possible to be produced from the compounds. Right? We are going to study only acid, base and salts. Now the question arises, how to identify that whether the given compound is acid or a base? So for that case, a theoretical part, hundreds of years back, not hundreds, even more than that, you can say it as 500 years back, there was a Robert Boyle who gave the first time the concept of acid base. He came out on the basis of the properties. He explained the given compounds are acid or a base on the basis of their properties. Now we have already studied it in our lower standard related to it. What are the properties of the acid? Acids are sorry test. Right? They turn blue litmus paper red, right? And the third one, they react with base to form salt and water, right? We have already studied these things in our lower standard, so nothing is new for us at present. But step by step we will again realize something different. Now, base. Bitter in taste. They turn red litmus paper blue. They react with acid to form salt and water. Now, actually, when Robert Boyle studied related to this, there were only few acids well known. You can say that hardly some, like if I put it as an example, hardly 10, 20, 50 acids might be known to him. Right? But as the day proceeds, today we can say that thousands of acids are there. Each and every acid cannot be tasted. Like an example, if I ask you today, can we test HCl? No, it's a cyanide, it's a poisonous, it's an harmful. So it was difficult to go for it. So as the time proceeded, new and new acids were being discovered. As the new and new acids were discovered, there was new problems that were arising in it. All the acid or all the base cannot be tasted. Right? Not only that much, on the basis of the taste only we can't specify it, because there were the certain acids which did not taste particularly sour, but still they were acid. Some base were there which were not bitter in taste, still they were base. So as the time proceeded, the definition has to be replaced or has to be modified. Right? So the certain limitations of it, Robert Boyle, he was unable to explain those on the basis of their taste. There were a limitation. All the acids cannot be tasted, and if the acids or base were tasted, they were not having specific taste. That also made them to change it. Right? Second problem was blue litmus turns red or red litmus paper turns blue. That was on the basis of when your solutions are prepared in water. When your acid is dissolved in water. There were few acids or few bases which were discovered, they were not soluble in water. And when they were not soluble in water, they cannot give me the taste of litmus paper. As a result, what happened? As a limitation, the modification in the definition has to be done. So that modification was done by the next scientist, and that was named as R.G.Parikh. First of all, we are studying only the concepts. Later on, we will study ionic equilibrium, or what is an equilibrium, that will be established. So here at present, we are only studying acid-base concepts. Later on, the modification in the definition of acid-base were done by R.G.Parikh. What did he show? Acid, when dissolved in water, they produce H plus ions. When they are dissolved in water, they produce H plus ions. Base, when dissolved in water, they produce OH minus ions. That means, as an example, if we take HCl, when it dissolves in the water, it produces H plus, right? Cl minus. So HCl is acid. It produces H plus. So HCl is acid. Right? You can say it as an NaOH. When it is dissolved in water, it produces Na plus OH minus. As it produces OH minus, it's a base. Right? So like that, number of acids and number of bases you can go in for ionization when they are dissolved in water. They will produce H plus and OH minus ions. But specifically, if I ask you the question, what is the name of the compound? CrO3. Generally we write it as chromium oxide, but it becomes chromic acid. It's a acid. Now can it produce H plus? No. Let's take it as an NH3, ammonia. It's an acid or a base? It's told that it's a base. Does it have OH? No, it does not have oxygen at all. How is it going to produce OH minus? So like that, number of compounds were being discovered later on as initial definition was being modified by the R.G.Parikh. Again, R.G.Parikh, while he did the modification, it was not the 1 year or 1 day or 2 days through which it was being applied. Number of such type of acids were has still been discovered because after a long duration what the concepts was being there. Again in the previous one we told that it's not necessary that all the acids and bases they will be water soluble. Whatever the acids nowadays, organic acids, they are not water soluble. Organic bases are not water soluble. Then how can I identify that whether it will give H plus or OH minus? So that limitation also arises. So to overcome that limitation, right? Still the modification in the definition was required. So after the R&S gave out with the limitation that he can't explain why this is having it as a basic character though it does not have oxygen. That was the limitation for the R&S, right? Because he modified on the basis of water solubility. But later on, after R&S, still the modification was required because still R&S was having certain limitation. So that modification was done by Lorentz Bronsted. That modification was done by the scientist named Lorentz Bronsted. Now, what was their concept for the acid base? According to them, acid, the compound which donates H plus are acids, base, the compound which accepts H plus are base. So they changed their definitions. They modified the definition. They told that those compounds which donates H plus, they are acid. Compound which gains H plus, they are base. For that case, they gave out the reactions also, which are known as Lorentz-Bronsted reactions. HCl, when reacted with water, it produces H3O plus Cl minus. So H plus was donated. So this was acid. Here H plus was gained. So this is base. Right? In the same way, they took it as an example of NH3 also. When they took it, they found it that water donated H plus, it gets converted into NH4 plus OH minus. This made water to act as an amphoteric character. That formula shows that it can act as an acid as well as base. So water is an amphoteric component. But at the same time, one acts as an acid, one will act as a base. The same formula, if we now want to do it, we can say it as an NH3 plus HCl. It produces NH4 plus Cl minus. It donated, so this is acid. It gained, so this is base. Right? So according to their definition, one which donates H plus is an acid, one which gains H plus is a base. So the limitation of R&S was being overcome. That this compound, it does not have OH, still it's a base. The reason is it gained that electron. Right? So we get it as a Lorentz-Bronsted reactions. So now we also now want to find out that when the Lorentz-Bronsted gave out the reactions, they developed it as an those components which establish the equilibrium in the solution, right? And because of that equilibrium, the acid produces conjugate base and base produces conjugate acids, right? Let's see what are the acids and base theory for it. Like we are having it as a CH3COOH. It reacted with H2O. We know it that it does not 100% react with it. So in that case, what will happen? An equilibrium will be established. It will be producing CH3COO minus H3O plus. So this H plus is donated to H2O. So at present it is an acid. It's a base. Right? But in the reverse reaction, what is going to happen? It's going to donate. So this one is going to become acid. And this one is going to become become base. For the reverse reaction, and therefore we are writing it as a conjugate. We use the word conjugate acid and conjugate base. Right? See, in the reverse reaction, this is base, this is acid. So from this reaction, what we can say? Acid produces conjugate base. And base produces conjugate acids. Right? So acid produces conjugate base and base produces conjugate acids. Conjugate acids and conjugate base are strong in nature. Right? We'll discuss about that concept later on. But this is what the reaction has to be written. Similarly, if I want to write it for the base, let's see that is it applicable for the donor. We wrote it as a reaction NH3, H2O, NH4 plus, OH minus. It's a weak NH3 gained H plus. So this was acid, it was base. But now for the reverse reaction, what will happen? It will be donating NH4 plus will be donating OH minus. So this one is going to become conjugate acid. This one is going to become conjugate base. So acid produces conjugate base. Base produced conjugate acids. Right? Similarly, number of examples. In place of asking you to write it, they may give you write the conjugate base of the given compound. So what does it mean? It's an acid. They ask us question, write the conjugate base. So that means this is acid. Acid donates H plus. So what will happen? It will become conjugate base. Right? Now in place of that, if they write it as, write the conjugate base of this given compound. So what will happen? Again this one will become acid. At that time it will become HPO3 minus 2 conjugate base. HPO3 minus 2 when we are having it, 4. If we are donating it, we will be getting it as a PO4 minus 3. So these can produce different conjugate acids, different conjugate base. Right? Vice versa. It's not necessary that they will ask you like that only. Right? HPO4 minus 2. Right? Conjugate base. So we wrote it as here. Now we will take it as conjugate acid. I want to write the conjugate acid of this compound. So what will happen? I have to add H plus. So what will happen? It's a conjugate acid for the same compound. Right? So acids are converted into conjugate base, bases are converted into conjugate acids. So like that, different examples can be given to you. Then one more example. Write conjugate acid of the given compound. I want to write the conjugate acid only. SO4 minus 2. What will happen? HSO4 minus, HSO4 minus, H2SO4. Right? So like that, conjugate the questions can be there to us. Write conjugate acid, write conjugate base, classify the given compound into conjugate acids or conjugate base. Right? Like that the questions can be there for acid base. But again, the problem, still there was a certain limitation for the lower Prost also. There were the certain acids, like example that we took chromic acid. It does not have H plus. How is it going to donate H plus? Right? Particularly an example, ALF3. It's an acid or a base. It's not a salt. Right? So now what to do it? So it must be considered that it's an acid. Right? How to prove it? Similarly, BS3, NS3, it was considered to be as a base. We already proved it that it's a base. But I am going to prove it now. This is acid. Right? Is it going to donate H plus? No. BS3 is not going to donate H plus. It's already there with a deficiency of electrons. Right? So at that time what happened? There was another scientist named as Lewis who changed or modified the definition for the acid and base, which are implemented till today. They are still not changing its definitions. That definitions are common at present also. Right? So whatever the new acids are still discovered, they are able to obey these rules. Acids are the compounds which accepts pair of electrons. Acids are the components which accepts a pair of electrons. These are the compounds which donates pair of electrons. A moment ago we took this as an example. BH3, boron. It's having only 3 electrons in its outermost orbit. When it is sharing those 3 electrons, it will have only 6 electrons in its outermost orbit. Right? Deficiency of electron. It gains a pair of electrons from the nitrogen. Nitrogen donates a pair of electrons. It's an electron pair donated by the nitrogen. So the component which donated a pair of electrons was base. We know NS3 was also a base according to Lorentz. But BS3, according to Lorentz or Arrhenius or Robert Boyle, it was difficult to answer it whether it's an acid or a base. So to overcome that answer, now we are having it gained a pair of electrons, and therefore BS3 is Lewis acid. Right? Is it clear? So these were the acid-base concepts, and on the basis of these acid-base concepts, we have to go it for the next step. But we will study those things in our next lecture. Till then, thank you.